All right, are you guys ready for this? Have you turned in homework 5? The PID controller stuff? Okay, it's due today. So the next one is the accelerometer. I'm pretty excited about this because a couple of projects I'm working on right now is using this accelerometer. So I can tell you the applications, for example. So the balancing vehicle, balancing car, two-wheel balancing car you saw last time. It's just controlled by one single accelerometer sensor on the car, and it's a highly integrated module. A little tiny sensor has a 3-axis accelerometer and a gyroscope, just in one little tiny integrated circuit chip. And the technology to fabricate this type of chip is called MEMS, micro electrical mechanical uh, chips or something, right? Or systems. So if you search for MEMS, you'll see a lot of SEM pictures. So all these little things, they are micro machines, in the macro level, not a real metal chain like this. So they use photolithography to fabricate different layers of materials on a silicon wafer or something else, any type of super smooth substrate. And they can make all these little tiny gears in micro level. So probably the little tooth of this gear is like only tens of nanometers, right? Is that amazing? So based on that, you can imagine, because all the integrated circuits are based on CMOS or wafers, if you have a little mechanical system can be fabricated on the tiny footprint on the substrate, and whatever being generated from there, any kind of analog signal, can be directly collected by the electrical circuits, which is also integrated on the chip, just within one single chip. And that's why the accelerometer we are using so it definitely has all these mechanical structures, right, inside. And at the same time, after that motion being detected, it's literally a capacitive sensor inside, because whenever the system moves, there are several electrodes inside, and the distance between the metal plates are being changed, so the capacitance is being changed. So you can develop a little capacitive sensor in the chip to detect all these capacitance changes and convert it into a digital signal. So in the past, probably all these accelerometers, 20, 30 years ago, it was not highly integrated like this. So the MEMS is just MEMS, nothing else. The mechanical structure being fabricated in the macro level on the chip, and maybe the capacitance signal being delivered to the pins of the chip, and you still have to use a capacitive sensor to detect the capacitance change and then convert it into digital. Since now everything can be highly integrated into one single chip. That's why if you look at the MPU 6050, you go to that tutorial. So this guy, this little thing has everything inside. You couldn't see what are they, but it has a mechanical system in the micro level, nano level inside, which can convert the motion, any movements of the system into capacitance changes, and then convert that capacitance change into analog signal and then digital, all together and quickly. So the mechanical system can detect any movements, accelerations, rotations, which is a gyroscope inside, and output is digital. So it's nothing but a digital protocol. And the name of the protocol is called I2C, or I square C. I, letter I, 2, number 2, and C. So that's the name of the communication protocol. It's a very standard digital communication protocol. You probably haven't used that before, right? I have two groups. I just got confused sometimes. I don't think so, right? So the first time you are using I2C protocol, and normally every single microcontroller, the modern microcontroller will have an I2C block. It's a digital block inside. It's a sequential logic block. So whenever the signal comes in, it is able to have a handshake. We're able to see everything just now. Okay, you're starting. Almost every single type of modern microcontroller has an I2C module in there. So um, one of the most important outcomes of this course is whenever you see a pinout of a microcontroller, you should be able to tell if this microcontroller has I2C or not, because there are not too many standard communication protocols. So I2C is one of them, and there will be UART, SPI. We'll talk about that later. But now just look at the pinout of this module. So scroll down to the module before this can display anything on the projector. See that right now? If you can see SCL and SDA, that means it is using the I2C protocol to communicate. Keep in mind, SCL, CL means clock, DA means data. So only has two lines. One is trying to synchronize the clock between the two devices. Another one is sending the data or receiving the data. Okay, so for digital communication, not wirelessly, but just with the wire, with the cable, you need a protocol for completing all these conversations. It's something like when I'm talking to everybody in the classroom, if I'm just saying, did you have breakfast? I mean, you don't know who I'm asking, right? So that's going to be a problem. So I have to say, Nick, have you ever had breakfast this morning, right? So you know I'm talking to you. And it's the same thing about the communication protocol, because I2C has a really big advantage of controlling multiple sensors at the same time. And you need to, whenever you are trying to start a conversation, you need to code the name of that person. So, which is when you are trying to communicate with a digital device, you have to send out the address first, which is the name. So you can think about, imagine the name of the person is the same as the address of the device. So you can have multiple different sensors, but they have different addresses. And then whenever you are trying to get the signal or data from anyone of all these sensors, you can just send out the request, which contains the address in there. So that sensor will know the computer system is trying to get data from this sensor, but not others, right? So that's one of the advantages of using I2C, which is you can have sometimes up to like 100 sensors in the system. And all these sensors are called slaves in the system. So for example, this MPU 6050 module is a slave. And if you have a microcontroller, it's sending requests to different slaves. That microcontroller is called master. So the master can send requests to different slaves and get a signal from the slaves. So the slave doesn't have to be an MPU sensor. It can be all different types of sensors as long as it has an I2C module in there. So it's the same as you have that kind of function in your brain, which is you understand English, right? If I'm talking Chinese, you won't be able to understand that because you don't have that I2C block. You don't have that kind of language function in your brain, which is equivalent to I2C block in a chip. So you guys have I2C, you guys have, you know, the English core, the English part in your brain is part of the brain cells is controlling this kind of function. So we can talk. Because pretty much every single modern MCU, the controllers, have the I2C block in there. So if you have an I2C slave, you can use your microcontroller to talk to that specific slave. And there are so many other sensors are using I2C as well. So if you need to detect accelerometer or acceleration data or gyroscope data, it's actually the rotation angular velocity. So that's from the gyroscope. So one master, and you have an ICL, SDA, and you can have an accelerometer, a temperature sensor, any other sensors to be connected to the same SEL and SDA. So the way to tell, which sensor you are trying to get the data from is just to send the address first, the correct address of that sensor first. So that sensor will respond to the master, but not others. So literally only two lines, data lines in the bus. One is ICL, one is SDA. Okay, keep in mind, important. This is, for digital communication protocol, this is one of the most important topics in microcontrollers because the reason you want to use microcontrollers, one of the most important reasons is it is able to communicate using standard communication protocols like I2C, SPI, UART, serial, all these kind of things. That's why it's so convenient. If you have since all the sensors and microcontrollers are using the same standard, it's going to be I2C. You just buy an I2C sensor and can just connect the two wires and use the library in Arduino. You can start a digital communication in seconds. Very easy. So let's take a look at the bus first. So that's the I2C bus. So the master is normally a MCU. So the MCU has a ALU inside or CPU inside. So whenever the data is being acquired from the slave, it is able to process the data. The MPU sensor is just a MEMS system with all this accelerator and gyroscope inside, but doesn't have a CPU, which means you cannot use the MPU or the slave to process the data. Whenever the data is generated, it's just digital signals, nothing else. You couldn't do addition, subtraction, multiplication, division, all these kind of operations. But if you send all the data from the slave to the master, like with microcontrollers, they have CPUs inside. So the data can be post-processed and be transferred to somewhere else if you like to the IoT website, third-party website like ThinkSpeak, or to another MCU, or to your laptop, right? All these different places. If you have a CPU inside, you are able to program it and make this happen. So the slave can be a sensor and also can be a microcontroller as well. So keep in mind, all the I2C protocols are standard protocols. They are just a specific digital block in the chip, inside the chip. So I can have an MCU and two wires, SCL and SDA, to talk to a slave, which is, CPU free, but also has a I2C block inside, so I can get data from this. And also, you can get rid of that sensor if you have two MCUs, two microcontrollers. As long as they have I2C modules inside, you can just short ICL and SDA together, and you can talk. So the two MCUs can talk with each other within the I2C protocol. Okay? So this may have some important applications in the future, because if all these MCUs are low cost, like $2, so it doesn't have that many functions inside, just one core, couldn't do too many interrupts. So if you have one MCU is doing all these things like acceleration detection, temperature detection, and also sending signal to the any of the third-party website, all this kind of works. But you also want to display the temperature data or any kind of data on the LCD display module. So probably one MCU is not good enough. These are too many things to manage. So in that case, you probably want to use another MCU to manage the display only, but the downstream MCU is doing all the other detections, talk to sensors. So you can use this MCU to talk to the other MCU using I2C or something else. It can be I2C, can be SPI, can be anything, but as long as you connect this SCA to SDA to SDA, SCL to SCL, they will be able to talk because they have the same language inside their core. Okay. So one quick question. How many lines for I2C communication? How many wires? 2. What are they? What's the name of the pin? Yeah? I remember that? Great. So I2C communication sends bytes. So it sends 8 bits, 8 bits, 8 bits as a package. So it's being organized, not like just keep sending the digital signals. It's being organized. That's why it's called a protocol. It's a standard protocol. If you look at here, there will be a start condition, and then followed by an address frame. So which is a couple of binary bits, which will define the address of the slave. And then there will be an acknowledge bit, meaning that the address has been sent. So which means it's working, it's been received, and there will be an acknowledge bit. Oh no, the read and write. So you need to send a signal. There will be one bit to define if you want to read or write to the slave. It's something like you have a master, you have a slave, and if I'm talking to Nick, for example, when I'm calling, I'm saying Nick, and I want to talk to you. So your name is equivalent to the address here, right? Then I'm gonna say something. If I'm asking a question, which means I'm trying to read some information from his brain. That sounds weird, but that's as Nick, did you eat breakfast? So did you eat breakfast is equivalent to that single bit. So I'm trying to request information, which means it's called read. It's a read request, right? So if I ask a question like that, which means I'm trying to read information from Nick, right? However, if I say, Nick, do this and do that, right? For example, just do the homework. I'm trying to write information to him and to let him do something, right? So that's it's not I'm trying to get anything from him. I'm not getting anything from his brain. I'm just telling him, like sending him a command, so he hears that and will save that command into the memory and just do something afterwards, right? So that's like a write request. And read and write, you need that single bit. It can be a 1 or 0. I think I forgot. Sometimes 1 means write, 0 means read, right? If after just follows this address bits package, and if there's a 1 after that, that means write. If there's 0, that means read. But can be different, depends on different systems. But just let you know, there will be 1 bit to define what's going to be done for the next step. If, think about that, if I'm doing a read operation, then after that, the sensor is going to start sending signal to me. It's like a person is going to answer that question, right? That's how you do a conversation. If I send a read request, then the person is going to respond with his or her answer, right? So whatever following this, it's going to be the answer from the person, which is equivalent to the data in the sensor. The sensor has been detecting the data and saved in the buffer or memory in the sensor. So the sensor knows what to be sent to the person who asks that question. That's how you can complete a conversation like that. I send a read request, and that sensor or that person is going to tell me the answer or give me that signal being saved in the sensor. So that's a read request. If you are doing a write request, so you can configure the different functions in the sensor. For example, for this sensor, accelerometer, when I'm trying to do a write operation, I'm actually telling, I can set up different functions, different configurations in the sensor. For example, the sensitivity, the resolution, the speed of the communication, all these kind of things. They're being saved in a certain register, which is like a control register. If you write a command into that register is going to define the behavior of that sensor. So it's just adding more functions to it. You can control, even though the sensor does not have a CPU inside, but you can set up the different configurations by using the write operation to change the behavior of the sensor. Okay. For this accelerometer, you can change the sensitivity or the range of the detection. So accelerations unit, we normally use G's, gravity, right? So how many G's? And there's a register you can configure, and you can change the range to be 0 to 10G, or 0 to 2G, 0 to 4G. I think it's plus minus, not 0 to. So it's going to be minus 4G to plus 4G, minus 2G to plus 2G. So why do you want to set up the range? I mean, why it's meaningful? Why it's useful? Can you imagine? So the sensor is going to detect this type of signal, but I want to tell the sensor to, because for example, the sense where the sensor will be installed will never get into 5G. So I mean, because I know the situation, the condition in the environment, it just never get into 5G, not mention 10G. So the maximum acceleration can be reached is going to be like 4G. So you definitely want to use 4G as a range, but not 10G. Why is that? I mean, if you say like, I just don't want to configure that range, I just directly use 10G, so it can cover all the situations. Why you don't want to do that? You want to minimize the range. Noise? No, not really. So the analog to digital converter inside the chip has a specific resolution. For example, here's the entire range the sensor can detect from 0 to 10G. And the application in that environment can only reach like 4G. So the signal will swing within 4G, will never go beyond 4G. but have a range set up here, you are losing resolution. You know what I mean? You're not using this part. It's wasting the resolution of the ADC. It's analog to digital converter. You have, for example, the 10G as a range, and it's a 10-bit. It's a 10-bit ADC inside. So the 10-bit ADC divide the 0 to 10G into 2 to the 10th steps. So every single step is 10G over 2 to the 10th, because 2 to the is 1024 actually. So it's 1024 steps for 2 to the 10th. So it is trying to resolve the 10G range using 1024 steps. So what's the resolution here? It's 10G over 1024. Anything lower than that cannot be resolved. So which means it's not really sensitive, right? I mean, if there's any minor changes which is smaller than 10G over 1024, the sensor will not be able to detect it. So just change the range to 0 to 4G, and you still have the same ADC in the chip. So the resolution will be 4G over 1024 for every single step. So you can tell the resolution, the sensitivity is way better than the previous one, at least as twice as much as the previous one. So, that's why you have to know what's the maximum value or the range can be possible in that specific application. Then you have to configure your sensor to just operate within that range, so you can have the best resolution. All right. How do you set up the configuration? Read or write? In terms of my MCU, how to set up the configuration? Read by reading or by writing? Right. Why is right? Should be right. So that function is being set up inside the chip. There is a memory inside, like a 1 byte, 100010, blah blah, whatever. So it's going to be a code to set up. It's 4G, 10G, 5G, 2G, right? So you have to tell the sensor the code. So you have to write into the sensor, right? So first, I'm going to send a command and call the address. This address. So that sensor will say, hey, I'm here. And then I'm going to write inside, write the code into it. So to let it know the configuration. Do I want to do 4G, 5G, or 10G as a range? Okay. And after that, what you want to do after that? So let's think about all these procedures for this communication. It's not really complicated. Okay. So for example, I'm the MCU, and here is the accelerometer sensor, right? I'm trying to talk to that sensor. So what is the first step? The very first step. You just think, what's the most reasonable first step? It should be. Yeah? The address, right? So I'm going to start a conversation and send an address. And what's next? So the sensor should acknowledge that. You know? So, hey, I'm here. It's just 1 bit. Look at the acknowledge, ACK. It's just 1 bit. Hey, I'm here, right? And what's next? So I'm going to do a write operation, because the write operation is already within the address. So within the address, there's a bit already set up as a write. because you need to do a write operation at the very beginning. So you can configure the sensor, right? So the sensor says, I'm here, and then I'm gonna start write to an address inside the sensor. So there are so many different memory banks. So they save all the different code in every byte memory bank inside the sensor as a configuration for the sensor. So I'm going to start writing something into that register. Just write a byte, just put a 1 byte in there, saying, hey, configure this as 2G as a range. All right, after the 8 bits or 1 byte has been sent to the sensor successfully, like boom, 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 8 bits, done. And the sensor is going to acknowledge it. Hey, done. 1 byte, done, received. All right. And what's next? I should do a read request. Read from where? From the any of the data banks inside the sensor. So the sensor will start sending all this acceleration data to me. All right. But every single step is completed by 1 byte. So you have to start it and end it for every single byte. It's interactive operation, precise. You tell something to the sensor, and sensor will respond with something. And the good news is we do not have to program every single step within the in the protocol. So the library can do pretty much everything for us. We just need to set up the address, and you use the library, the functions to read and write from the sensor. It's pretty simple. So let's look at the process first, the details of the protocol, so you know what's going on. So the steps of the I2C data transmission. So you can tell that I have one master, but I can have multiple slaves at the same time. So here is the data. So they must have the same data because they are using the same wire. You know, for the same wire, you cannot have different voltages, right? If you put high, it will be high for everyone because it's the same wire. So if you can see here, they are all the same signals, right? So the first step, 0, 1, 0, 1, 1, 0, 1. So that's the address. That's the address of the device. And RW, R/W means it's a read or write. So if you look at the data line over here, you know, clock is always clock, just boom, 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 this specific frequency is clock. You are not changing anything, it doesn't carry any information. So, but just look at the SDA line. It's 0. So 0 means what? Let's take a look. The master sends a start condition to every connection. That 0 means write. I mean, doesn't matter. I mean, it seems like it's right. It's writing the address. So 0, 1, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1, 0, 1. That's the address for this slave. So only this slave will respond to this address call. You can see all the other ones they have a different address. Okay, only this one will respond. So how it is able to respond? If you look at this chart here, keep in mind, all the ISDAs and all the ICLs, they are the same voltage node. They are being shorted to the same bus, right? Just two lines for everyone, for every slave, and for the master as well. Okay? You can see the first one, nothing. Nothing, the ISDA, no response. But only this guy, because the address matches with the address of this slave will pull the ISDA line to ground. I mean, do you think the master knows which one pulls the ISDA line to the ground? I don't think so. Because the ISDA line is being shorted to all the slaves. So there's just one of the slaves found out the address being sent by the master matches with its address, right? And then that slave will just pull the ISDA line down to the ground to tell the master, hey, at least one of us has the address which is the same as what you are calling, right? But doesn't matter if the master doesn't know which one is pulling, doesn't matter at all, right? So the ISDA is put to the ground. So all the ISDA lines will be ground for that short period of time. It doesn't matter because they are sharing the same ISDA. And after that, this guy is going to do whatever the master is telling it to do. Okay, so let's see the next. What's next? So it depends on the setup in the first byte. The master will send write request or receives the read request, receive something from the slave. Depends on the setup here, read or write. Okay. So it reaches here. So the data will be sent or being received by the master, but there will be something on the ISDA line. But only this guy will respond. Why? Will receive or send this data. Why is that? But all the other ones, because it's the same ISDA line, so it's going to show the same signal here as well. But why it doesn't matter for the slaves? It's not affecting anything. It's a state machine. It's a sequential logic in the protocol. Because these two guys didn't go through the process of that acknowledgement and pulling down the ISDA, so it's not going to that state. That's why it's not doing all the jobs, all the following jobs. Even though the ISDA line is being shared by all the slaves, it's just not receiving it or sending it. Even though there's a voltage, it's trying to oscillating at that pin, the metal pin of that slave. It's just not responding at all because it was not at that state, right? So remember the state machine in logic. In state one, if that one receives a 1, then jump to another state. And if that state receives a 0, then jump to another state and then do something, right? If the other slaves are not going through every single sequence or states, it won't be able to function as the one who has already go through all the states in the state machine. So it doesn't matter, even though they are sharing the same ISDA line, the other slaves are not doing anything. They just have oscillating at the pin, but the logic is not responding at all. Okay, so only this one will talk to the master. So after each data frame has been transferred, the receiving device returns another acknowledge bit to the sender to acknowledge the successful receipt of the frame. So just pull the SDA line down to the ground again as acknowledgement. To stop the data transmission, the master sends a stop condition to the slave by switching SCL high before switching SDA high. So the master is going to do something like this. Boom. But has to be before this. See? The master sends a stop condition to the slave by switching SCL high before sending that high. So it's not really obvious over here. Well, take a look at the timing diagram really quick. Let me see if I have it here. All right. Here. Nope. This one. So to start a conversation, the SDA has to be put down to the ground after the rising edge of SCL. So what's actually happening is the SCL, because the clock is going, is oscillating all the time. So it has rising edges and falling edges all the time. But how can you tell? How can you start that conversation? So the clock is doing this all the time, right? If you part it up, the clock is going to start oscillating. But the SDA line is pretty much nothing at the very beginning. Can be high, maybe. Always high, right? But the clock is always, as long as you part it up, doing this. So master slave already shorted for SDA and ICL. ICL is always oscillating, and SDA is high, for example, on both sides. So just pulling this up to the VDD. So when can you start that conversation? You need a start condition. So what is that start condition? So when the ICL is going up as a rising edge, and right after that rising edge, pull SDA down to the ground. So that's a sequential logic. That's a start condition. I know the clock is oscillating all the time, right? I know it. But before, so right after the rising edge of this clock, before it's going to the falling edge, in the middle, I pull the SDA down. So that's a condition you want to start a conversation. It's just defined by the engineers. You must find something to start a condition, right? You must start the conversation. So that's the definition for the start condition for I2C. Okay? You can design the sequential logic, it's a state machine. Okay? What's the stop condition? Here. You pull the SDA up to the power, and right after that, the clock, you are not pulling the clock to anywhere, but the clock. So you pull the SDA up to the ground, to the VDD, right before the clock getting to the falling edge. So that's the definition for the stop condition. So which means we're done for the first conversation. The byte has been sent or received successfully. That's one byte, done. So if you want to start another conversation, you have to do this again. Just need to know. You don't have to program it. Okay, you don't have to design the I2C sequential logic as well. It's not what we are doing here. So the application is way easier than this. Now let's look at the code. So one thing you need to know, the I2C requires two pull-up resistors. So you should pull the two lines up to the power. So pull-up resistors can be 10K, can be 5K, 4.7K. Normally that's what they are using, 4.7K. Okay. So you must be wondering why there are so many different values for pull-up resistors. If you are worrying about the speed of the communication really a lot, you probably need to engineer that a little bit, do some calculation. There are some guidelines to calculate it. Because you can imagine, if I have a different resistor, all the digital systems, they have transistors, which has, the capacitors in the metal plates. If there are some dielectric materials and metals, there will be capacitors. There are capacitors everywhere. And if you have a resistor capacitor circuit, so the bandwidth of the communication will depend on the resistor value and capacitor value. So the capacitor is not being changed; it's already designed in the chip. So if you change the resistor value, will change the current. Amount of current can get in and get out from the capacitors. Will change the speed a little bit. If you really care about the speed of the I2C, but normally, the I2C speed is always more than enough. So I don't really care. 4.7K, 10K, 5K doesn't matter. As long as it's somewhere around 5K and within 5K and 10K is fine. Let's pull it up to the power. So pull up ICN and ICL to the power. And the MPU module probably already have the pull-up resistor on the PCB. They probably already did it for you, so you may not need to do that. So take a look. If you look at just look at the ICL and ICA. Did you see 472? 472, what's the resistance? What's the resistance of 472? Did you see 472? Can you see 472? You couldn't see 472? What's the resistance? 472? No. It's 47 times 10 to the second. So 4.7K. Did I say 4.7K just now? Yeah, so 4.7K is a pretty popular pull-up resistor. So you can use 4.7K, 5K, 10K. I don't think there will be any difference. So on this PCB module, they already put up the ICL and SDA to the power. So don't need to do that. Okay. So whatever I did over here, I think it's a little bit extra. It's not doing anything. So if I put, oh, where? No. Let's take a look at the TCA. No, not there. Did I show you any schematic? I didn't, so which is fine. Okay, just keep in mind you don't have to add another extra pull-up resistor to the data bus here. So let's take a look at the code. Look at the code. Include wire.h. So the wire is the I2C protocol library for Arduino. and 68, so 0x68, which is a hex address for your MPU 6050 sensor. So that's the address. And float. So these are the acceleration data for 3 axes, x, y, and z. And then start the serial communication because you want to visualize the acceleration data in real time in your serial monitor. And where dot begin, so you can start the I2C protocol. And where dot begin transmission MPU, so you can send the address of the slave to the bus. So MPU is here. MPU, that's the address. And then write. Talk to the configuration register, but there's one thing is missing. So I'm recording, so you want to come back and check this out. So one thing you have to do at the very beginning is to reset the device. Very important. Keep in mind, I didn't include it into the first example because I already reset it in the past, so it's up running already. If you do not do this reset, your accelerometer is not going to start working. Keep in mind, okay? Do not send me an email a couple days later and, hey, the sensor is not sending anything. All right, you have to reset it first to activate it. So how to reset it? Right after you send the address of the accelerometer, you do this, where.write. This is a register or memory or configuration memory inside the sensor. You write the address first, then write the value you want to put into the register. So the configuration register is a memory bank inside the sensor, and that register has a specific address with it. Okay, so when you want to put something into the register to configure your sensor, you have to write an address for that register first. It's not the address for the sensor. It's the address for every single register inside. So memory address, right? So 6B is the address of that register. And then write a 00 into it. It's a reset command. So activate the sensor. And end the transmission, true, end it. 1 byte, done. Write command and write something in there, done. End it. Then start another conversation. Okay, let's go back to the first example. So keep in mind, before this guy, before here, reset it as what I just showed you in the second example, but I didn't have it here. It's already activated in the past. Okay, and after you reset it, you start another conversation, begin the transmission to the MPU, and write another address. So 1C is this accelerometer's ACCEL underscore config register. The address is 1C. So you need to configure something in the configuration register, second step. So you need to send the address first. So right after that, here's the data you want to put into the register. And I just blocked it. I can see if I want to do a plus minus 4G as a range, I need to look at the table here, right? 4G, I need the combination of this one to be 1. So let's find out that register. 1C. So that's 1C is the address of this acceleration configuration register, and definitely it's a 1 byte register. And you just want to set up this single bit. It's not single as the 2 bits, right? 2 bits to be 1. So don't worry about the other ones. Just 0 by default. It's going to be 0, 0, 0. If I need these 2 bits to be 1, 0, 0, 0, what's next? You are lost. You're totally lost. How many bits do I have over here for this register? 8, because it's 1 byte. And I need, since there are 2 bits over here for this 2 bits spots, and since I know I want to set up these 2 bits as 1, so I can get a plus minus 4G range. So I need here to be 1, right? So tell me what is this hex number? 0x what? 0, 0, 0, 0, which is 0 for the first 4, for the upper 4 bits. And now for the lower 4 bits, what are they? 8. Because 1, 0, 0, 0. That making sense? So I want to write 0, 8 to 1C, which is a configuration register. So after this, after I send the address of the register, I want to set up what over here? Come on. 08. And then, the same concept, blah, 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 request from this address for 6 bytes. 6 bytes. Why 6 bytes? You can see from register 3B, 6 bytes, 1, 2, 3, 4, 5, 6. So all these data can be requested at one time. These are, see, the acceleration for X and acceleration for X as well, but it's from the bit 15 to 8 and the bit from 7 to 0. So actually, you have to combine these 2 bytes into one 16-bit data as that X as a acceleration as the X-axis. So the data is actually 16 bits, but sending 1 byte by 1 byte. So I have received 1 byte first, which is being saved in 3B as the upper 8 bits in the 16 bits, and the lower 8 bit, and combine them together. So this is how you combine them. This is how you combine them. You get the first 8 bits, left shift by 8 times, and then OR the lower 8 bits. Just OR it. Boom, combine 16 bits. You have an apple, you have a pie, apple pie. Remember that? Apple pie. You have an upper level 8 bits, you have a lower level 8 bits. You combine them, you get a 16 bits X-axis data. Same for Y, same for Z. Then done, plot it. All right, so this is just a 1 week, and I hope you can get it done. But I think I will be able to answer some questions on Monday next week. And yeah, so it's due next Wednesday. I think I should be able to be done because it's really not really hard. If you have questions, you can ask me on Monday in the business building. All right? Okay, that's it.